So here are the solutions to Lesson 6, Explosions. The gunpowder explosion in a gun results in an expansion of gases that cause a bullet to be propelled forward. The gun, in turn, kicks or recoils backwards. The recoil momentum of a gun that kicks has to be the same as, because momentum is conserved. Whatever momentum the bullet gained going forwards, the gun will gain, but going backwards, so we'll call it negative. What about the recoil speed? Well, since momentum is mass times velocity, and the gun has so much more mass than the bullet, the recoil speed will be less than, which is a good thing. Otherwise, the gun would go shooting backwards. Or maybe it's a bad thing, because that would mean that it was much, much tougher to fight wars. Determine the missing velocities of the following objects or combinations of objects. Okay. I'll do these one at a time. First, let's copy the actual instructions. Donk. And then let's copy part A. Okay. I'm going to call this mass A. I'll call this mass B. There's a collision, so this is a job for conservation of momentum. The sum of all the momentum we start with equals the sum of all the momentum we finish with. Mr. Dueck, do I have to write that down? No, but for what it's worth, if it's a momentum question and you write that down, typically I'll give you a half mark just for writing that down because, oh, you recognized what the correct approach is. Before the collision, what's moving? It looks like just mass A because this one doesn't have a velocity attached to it. So I think it's going to look like this. The mass of object A, velocity of object A, initial, wham, they collide, and it looks like they stick together. And they want me to find V, that apostrophe, we actually say V prime, but that's definitely V final. So I think I'll just divide by the bracket. V final is going to be mass of A, velocity of A initial, divided by mass A plus mass B. Mass of A is 2, velocity is 5.2, divided by 2 plus 13. Definitely going to have to put brackets around the bottom. Technically don't need it on the top because we're multiplying. Now, I can already make some predictions before I even hit equals. I definitely know that if they stuck together, the answer is going to be less than 5.2. Way less than 5.2. 0.69. If you wanted me to add a direction, I'll say forward. B. Almost the same question, but it looks like they're both moving. So again, I'll call this mass A, I'll call this mass B, and they stuck together. This is a job for conservation of momentum. Looks like we're going to have mass A, velocity A initial, mass B, velocity B initial, stuck together. And again, we want to get the V final by itself, so looks like I can just go divide by that. Looks like the final velocity is going to be, now, mass A is going faster, but it has less mass. Mass B is going slower and has more mass. I think mass A is going to slow down. I think mass B is going to speed up, but mass A is, I think the answer is going to be between 4 and 6. Let's find out. It's going to be 3 times 6 plus 10 times 4 divided by 3 plus 10, or 13. Bracket 3 times 6 plus 10 times 4 divided by bracket 3 plus 10. 4.46. That seems right to me. C. Hey, yep, that looks, there you go. That's right, I forgot I'd done answers. C. C really looks similar to B, except here the bigger, faster one is hitting the smaller, slower one. I think and they stick together. I think in the final answer, the 3 kilogram mass is going to be going faster. The 6 kilogram mass will slow down. Again, I'm going to call this mass A, mass B. So I'm going to have mass A, velocity A initial, mass B, velocity B initial, equals stuck together. The final is going to be mass A, 10 times 6 plus 3 times 3, all divided by 13. I added them up in my head. I divided that over myself. That's a little messy, Mr. Dueck. Let us give myself some more room. Oh, lost a bracket. So here we go. Bracket 10 times 6 plus 3 times 3 divided by 13. 5.307, 5.3 meters per second forward. I'm adding a direction because they did say find the velocity, and I looked ahead at some of the questions and I noticed some are going backwards and some are going forwards, so okay. D. Okay. Now they don't stick together. Gotcha. So, again, mass A, mass B. So I'm going to have this. Mass A, velocity A initial. Mass B, velocity B initial. Wham, they collide. Mass A, velocity A final, plus mass B, velocity B final, since they're not stuck together. And I guess I am getting that by itself. I think I'm going to minus this over to that side, so I'm going to end up with mass A, velocity A initial, plus mass B, velocity B initial, minus mass B, velocity B final, and then I'll divide by mass A to get that by itself. And then if you don't mind, I'm going to put the VA final over here on the left because that's where we're used to seeing it. Here you go. Mass A, 10 times 6 plus 3 times 3 minus 3 times 9 all over 10. I might be able to do this one in my head. It's going to be 60 plus 9 minus 27. 69 take away 27 is 49 take away 42 divided by 4.2. I think it's going to be 4.2. forward or to the right. Boy, did I give you a bunch of these. E. Ooh, now we have some changes in direction. I'll have to let one way be positive and one way be negative. Cool, 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 cool. Mass A, mass B. So the equation is going to be the same. Mass A, V, A initial plus mass B, V, B initial. Mr. Dueck, shouldn't there be a minus? The minus will show up when I put in the negative velocity. Wham, they collide. And it looks like I'm going to have mass A, V, A final plus mass B, V, B final. And the question is suggesting that this, when I solve for it, should end up being negative. It looks like they collided head-on, and then this bounced backwards. Again, I'm going to minus this over to this side. In fact, you're going to notice it's really, really similar to the equation that we just finished doing on the previous question. I'm going to end up with mass A, VA initial, plus mass B, VB initial, minus mass B, VB final, all over mass A, that equals VA final. And ideally, this should give us a negative answer. Let's find out. Mass A, 3 times 3, plus mass B, 2 times negative 2, minus mass B, 2, positive 4, because the 4 meters per second is definitely to the right, divided by 3. I might be able to do that in my head. It's going to be 9. Take away 4 is 5. Take away 8 is negative 3. Is negative 1? Which equals 1.0 meters per second to the left or backwards. I should have said to the left. That's less writing. F. Okay. You know what? This is the physics of a rear-end collision, of a car getting rear-ended. Now, the smaller car is going faster. It hits a bigger car that's going slower. After the collision, the smaller car has slowed down. It's lost momentum. That means the bigger car has sped up. I can already tell you this answer is going to be bigger than 4. Mass A, mass B. Mass A, velocity A initial, mass B, velocity B initial, equals mass A, velocity A final, plus mass B, velocity B final. And it looks like we're trying to get that by itself. I think I'll just minus that over and divide by mass B. Trying to see why I taught you all that formula manipulation. Can you imagine trying to memorize all of these different variations? Oh. Some teachers do it that way. Not me. Here we go. Mass A, 3/6. Plus mass B, 5 times 4, minus A, 3, and then 3.5, divided by mass B. 3 times 6 plus 5 times 4 minus 3 times 3.5 divided by 5, and I get 5.5 meters per second, even, and that's going to be, since I got a positive answer, forward. Cool. Number 3. So the key here is to realize initially at rest, what that means is the initial momentum is 0. This is going to be a conservation of momentum question. The sum of all the initial momentum equals the sum of all the final momentum. But the initial momentum is 0, which means the final momentum is also going to be 0, but that's going to be mass TED, velocity TED, plus mass Larry, velocity Larry. I'll use T and L instead of A and B since they gave me lovely names there anyways. They want me to find the final speed of Larry? Okay. Let's see if I can do this in one step. V Larry is going to be negative mass T, velocity T, divided by mass Larry. Negative is going to be mass TED 40, TED 6, Larry 60. Oh, I can do that in my head, I think. Yeah, this is going to be 40 divided by 10. I get negative 4. Now they wanted just the speed, so 4 meters per second. The negative just means it's in the opposite direction of Larry, or the opposite direction of TED. Number 4. We used to do this when I was a kid all the time, try and balance. We had out on the lake on an inner tube, and then you would try and stand up, and then you would try and dive off, and you always ended up belly flopping because when you tried to dive forwards, the inner tube had to move backwards because both you and the tube, your initial momentum was 0. But because the tube had so little mass compared to you, the tube would always shoot out from underneath faster than your body was trying to dive forwards. So there, that explains that childhood activity. We're going to say this then. 0 momentum equals mass. Ooh, we have Robbie and Raft. I'll call this mass A. I'll call this mass B. They both begin with R. So mass A, velocity A, plus mass B, velocity B. And you're going to notice this is identical to the question we just did. If I get the velocity B by itself, I'll get velocity B equals negative mass A, velocity A, all over mass B. It's going to be negative 79, 2.4 divided by 24. Oh, I can do that in my head because the 2.4 divided by 24, that just ends up with a 10 on the bottom. It's going to be 79 divided by 10. It's going to be negative 7.9. Now, if I call north positive, then the negative is going to mean south. So it's going to be 7.9 meters per second at south. And again, you can see Robbie dove forward at 2.4. The raft went backwards way faster. It went out from under his feet. He probably belly flopped. Number 5. A bomb explodes into 2 pieces. A 12-kilogram piece flies off at 145 meters per second due west. What's the velocity of the other piece? This is the same question that we just finished doing because let's assume before the explosion that they're both at rest. our initial momentum is 0. I'll call this mass A. Oh, hang on. I'll call this mass A, and mass B is going to be 38, take away 12 is going to be 20 kilograms. Nice try, almost fooled me there. Boy, that's messy. So, let's see. 0 equals mass A, velocity A, plus mass B, velocity B. I want to get that by itself. Oh, I accidentally erased the whole thing. I want to get that by itself. So how will I do that? Negative mass A, VA, divided by mass B, that equals the velocity of B. Now, if I call west negative, if I get a negative answer, that'll be west. If I get a positive answer, that'll be east. So I'll call this negative. Here we go. Negative, mass A, 12, negative 145. Ooh, I'll get a negative times a negative, which is a positive, so I'm going to get east, divided by 20. Negative 12 times negative 145 divided by 20. Uh-oh, do I have a typo? Yeah, I can't do any math, Mr. Dueck. It's not 20. You've probably been screaming at me. Wow. 38 take away 12. Where'd the 20 come from, Mr. Dueck? 26, Mr. Dueck. Wow. Wow, wow, wow. Hopefully nobody watches this question for their solution key. 66.9 meters per second. I got a positive answer, so positive is going to be east. Are you sure? Yes, I'm positive. Bad joke. Number 6, football tackling is a great example of conservation of momentum, or a hockey body check as well, because those are good collisions. A 91-kilogram running back is sprinting due east at 9.7 meters per second. How fast must a 132-kilogram linebacker be running in order to tackle the running back? Assume the collision is head-on, and the linebacker holds on to the running back for the whole tackle. Okay, so if they hold on, they stick together. We're going to have this. I'll call this mass A. I'll call this mass B. And I'm going to call east positive. Before the collision, what's moving? Mass A and mass B, because they're running towards each other. And they stick together. It wants me to figure out how fast the running back has to be. Oh, by the way, actually, I know this answer. This is going to be 0, because the final momentum is going to be, we want to bring this running back to a stop. To a stop. So 0. So, really, I get this. Mass A, velocity A initial, plus mass B, velocity B initial, equals 0. I want to get that by itself. I can do that. I'm going to minus, so it's going to be this. The velocity of the linebacker is going to be the opposite of the mass times of the running back, velocity of the running back, and then divide by mass of the linebacker. By the way, notice the bigger this number is, the slower the linebacker can be. That's why the really heavy, slow guys, we put them up at the line, because they don't have to get going very fast, and they can still cancel out somebody else's momentum. So we're starting to explain why people play certain football positions. Good physics in football. Negative 91. Positive 9.7. all divided by 132. Negative 91 times 9.7 divided by, try that again, negative 91 times 9.7 divided by 132. And I get negative 6.69. And negative is west, so 6 points. Boy, I'm having trouble writing today. 6.69 meters per second west. Number 8. Ooh, cannon shell. Cool. A says, calculate the final momentum of the shell. Oh, okay, this is just plug and chug. Momentum is going to be mass times velocity. So final momentum is going to be mass times final velocity. It's going to be, of the shell, 20 times 180, which is going to be, I can do that in my head, 3,600 kilogram meters per second. B says, what's the magnitude of the momentum of the cannon immediately after the shell is fired? Let's assume that the cannon is initially at rest. Well, if the shell gained 3,600 kilogram meters per second, then the cannon lost 3,600 kilogram meters per second. Now, it just asks for magnitude, so if you left the negative off, I wouldn't freak out. But I do know they're in opposite directions. C says calculate the recoil velocity. Okay. Well, negative 3,600 equals mass of the cannon, velocity of the cannon. So velocity of the cannon is going to be negative 3,600 divided by the mass of the cannon, which was 850. Negative 3,600 divided by 850 divided by Mr. Dueck. And I get negative 4.24. So the negative means backwards. Skip number 9. Number 2, astronauts. I like outer space thought puzzles, because when I grow up, I want to be an astronaut. Suppose there are 3 astronauts outside a spaceship, and they decide to play catch. All the astronauts weigh the same, so same M, and they're equally strong. The first astronaut throws the second one toward the third one, and the game begins. What's going to happen? Okay, well, as soon as this astronaut pushes this astronaut, let's say with 5 meters per second, because they have the same mass, this astronaut will rebound backwards at 5 meters per second. Now, this astronaut is going to travel forwards. When they collide, they'll now be moving backwards at 2.5 meters per second, because they'll stick together. Their mass will double, so the speed will go in half. So they're moving backwards. There's no way this astronaut can throw this astronaut forwards, because if he pushes them... Anyways, you can read what I said here. Call the astronauts A, B, and C, where B is being thrown. After one throw, A is going to be moving backwards far too fast for C to throw B hard enough to reach A. If astronaut A pushes astronaut B as hard as he or she can, then the game's over. Because they'll be moving backwards. Even if this astronaut pushed astronaut B forwards at 5 meters per second, because they're going backwards, their relative velocity would be positive 2.5 meters per second, which will never catch to the left, which will never catch up to the 5 meters per second to the left. So playing catch in outer space would be tricky. I think that was it. Yes, it was. Oh, no, I stand corrected. I gave you a nasty question. Why did I do that? Because I'm mean. Shut up. But I am. Cool. What's the nasty question, Mr. Dueck? $1,200-kilogram car moving at 35 kilometers per hour. Nice try. 35 divided by 3.6. I should have made it 36 divided by 3.6. So that would have worked out to 10. But 9.722. Runs into and sticks to a parked car. The collision takes that long. After the crash, the car wheels lock and they skid to a stop. Ooh, coefficient of friction. So A says, find the speed of the cars immediately after the collision. I'll call this mass A. I'll call this mass B. And now we're doing some actual accident investigation. Okay? This is what the RCMP would look like. Well, before the collision, I know mass A was moving. After the collision, the cars stuck together. I'd like to know right after the collision how fast they started to move. Okay. V final is going to be mass A, V, A initial divided by mass A plus mass B. Mass A, 1,200. 9.72, I'm going to use my answer button, divided by 1,200 plus 1,000. 1,200 times answer button divided by 1,200 plus 1,000. And I get 5.3 meters per second, 5.3030. So 5.30 repeating meters per second. B, the distance traveled before skidding to a stop. Ooh. Okay. Well, since they want me to find a distance, I'm going to go D equals question mark. Skidding to a stop, V final is 0. V initial is 5.30, repeating my answer from A. You know what? If I could find the acceleration, I'm good to go. The time they gave me in the question doesn't help me because that's the time of impact. That's not the time it took to come to a stop. How come? Oh, this is a job for a free body diagram. Here are the cars. Forces acting on them are gravity, normal force, and if the cars are skidding to the right, friction is what's bringing them to a stop. In fact, friction equals ma. Mu times the normal force equals ma. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. Mu mg equals ma. Conveniently, now this m is the mass of both cars stuck together, but conveniently, they'll cancel. If I divide the m over, it'll cancel the other m, which is nice. And I can tell you that a equals mu g. That's the acceleration if an object is skidding to a stop and there's no other outside forces. So I can stick that right there. I'll get d equals vf squared minus vi squared all over 2a, 0 squared minus 5.30 repeating, squared, I'll use my answer button, divided by 2 mu g. I have to do one more thing. This is going to give me a negative answer. Actually, this acceleration, because we're slowing down, it's negative. So I'm going to put a negative in there, because we're slowing down. 0 squared minus answer button squared divided by bracket 2 times negative. Hey, what's mu? I don't know. What's mu with you? 0.4 times 9.8. And we get 3.59, 3.6 meters. Okay? Now, in real life, what you would do is you would measure the length of the skid, and that's how you would get this distance. You would be investigating afterwards. But if you knew the length of the skid, could you solve for VI? Yes. And if you knew VI, could you solve for VI right here? You could actually work your way backwards and figure out how fast the incoming car must have been going. And you could prove that in a court of law using physics. So if a driver claimed they weren't speeding, you would be able to prove yes they were or no they weren't. Oh, there's a part C, impact force. Oh, that's easier. Impact force. I think I'm going to use impulse. Okay. And I'm going to use the impulse on car A. I could also do it on car B because forces come in pairs. I'm going to do it on car A. Easy peasy. So, let's see. The change in momentum for car A was its final velocity was 0 minus its initial velocity. That equals force times time. So the net force is going to be 0. Thought I changed colors, Mr. Dueck. The net force is going to be 0 minus car A was 1200 and 9.72222. Is that right? Yeah, 1200, 9.7. 1200, 9.7222222. All divided by time, which was 0.15. The force on car A is 0 minus 1200 times 9.7222222 divided by 0.15. Make a typo here, Mr. Dueck? Yes, I did. Sorry, I want the impact force on both cars. And that means the final velocity is not 0. Silly me. Silly me. Dumb. In fact, I'm going to instead do this on car B, because car B does have an initial velocity of 0. This is what I should have done. I should have found, sorry folks, F on car B. It's going to be impulse equals force times time. Impulse is going to be mb vb final minus mb vb initial equals force times time. VB initial is 0 because the car B started at rest. VB final was, we calculated in part A, 5.30. That's what I should be doing, Mr. Dueck. So, force is going to be mass of car B, velocity of car B final divided by time. Force is going to be mass of car B, which I think was 1,000. Yes, it was. Velocity of car B, 9.72. Is that what it was? Repeating? Divided by 0.15. Sorry, I did that totally wrong initially. Times 9.7222222. Let's see if I did this one wrong again. What am I doing wonky here? Pause the video for a second while my brain moves out of a rut. Dumb mistake again, didn't I? You probably all caught it. It's not 9.72. That was car A. The initial velocity of car B after the collision was 5.30. Wow, am I butchering this question? But I'll leave this in to let you know that I make dumb mistakes too. And there we go, 35,000 newtons. Wow, did that take a while. Sorry about that. Oh, hey, wait a minute, I'm not sorry. It's a nasty question. What does a nasty question mean? This is way tougher than I would ask you on a test, maybe as a bonus question, but I'm also always trying to show you where we use this stuff, and especially Part B and Part A is a nice application of RCMP crash investigation. You could actually start with the distance and reverse this question and end up being able to figure out how fast car A was going before it hit car B. Hope that helps. Take care, my angels.